In this video, we are going to continue solving statically determinate structures. For all problems, we're going to assume counterclockwise as our positive movement, left to right as our positive for horizontal components and reactions, and going up as our positive for vertical reactions. For our first problem, we need to find our reaction forces at A, B, and E. Okay, let's draw the free body diagram for our first section. We're going to analyze A through C. We're going to have a vertical force at A, and we're going to have another vertical reaction at B, and we're going to have vertical and horizontal reaction at pin connection C. We have a concentrated load being applied in between roller point A and B, which is 6 kilonewton. Now to solve, let's take moment about the point C. First point we encounter is B, which is Py. It's clockwise, therefore negative, and it's 2 meters away. Then we encounter our external load. It's 6 and it's 4 meters away from point C. And finally we have our vertical reaction at A, and it's in clockwise direction, and it's 6 meters away, all equals to 0. Solving this equation, you get 6ay negative by times 2, and all equals to negative 24. I'm going to leave it here for now. Now we can see that we can't do anything else for this section. Let's do our section CD. For CD, our free body diagram is as follows. So we're going to have horizontal and vertical reaction at C. Then we have a distributed load, which is going to result in a concentrated load 2/3 away from C. And then we have horizontal and vertical components at D. We are not going to include the concentrated load at pin D because it's being stated in the question that it's right next to it, but it's not on pin D. Okay, so let's find our concentrated load for the triangular distributed load on member CD. It's going to be half times 6 times the distance, 3 meters. This comes up to 9 kilonewton, and it's 2/3 away from C, therefore it'll be 2 meters away and 1 meters away from D. Okay, let's take a moment about the point C again. First we encounter clockwise reaction from our concentrated load, 9 kilonewton, and it's 2 meters away from C. And then we have a vertical reaction at D, and it's 3 meters away, all equals to 0. Solving for dy, we get 18 divided by 3, which is equal to 6 kilonewton. Another thing I did not do at section C, because we know that there's no horizontal reaction forces acting on it, we know that Cx is equal to 0. If Cx is equal to 0, looking at a free body diagram of CD, we can see that dx is dependent on Cx, therefore dx is also equals to 0. And now we can find the value of Cy by adding all the vertical forces. We have concentrated load going downwards and our vertical reaction at D going up, so it's positive 6 kilonewton, and then for Cy it's going downwards, therefore negative. Solving for Cy, we get 9 take away 6 is 3, negative 3 comes over the other side of the equal sign and becomes positive 3 kilonewton. Multiplying the negative sign on both sides, we get negative 3 kilonewton as our solution for Cy. Okay, now that we have value for Cy, we can go back to our section AC and solve for problems, solve for our solutions. So first, because we have Cy, we can sum the forces in the y direction. So we're going to have positive AY, positive BY, and positive CY take away the point load that's pointing downward, and it's 6 kilonewton, all equals to 0. We found the value of Cy, and we can manipulate our value from this equation here to get value for BY with respect to AY. It's going to be negative 24 positive 6AY divided by 2, which is going to be, and it's negative 2. And solving this, we get 12 and 3. And we get positive 12 and negative 3y. Okay. So our AY is going to stay as it is. Our BY will be 12, take away 3y divided by nothing. Plus our CY we just calculated, it's going to be negative 3 kilonewton, take away 6 kilonewton, all equals to 0. Solving for AY, you get negative 3 divided by negative 2, which comes up to positive 1.5 kilonewton. That's our solution for AY. Now let's solve for our section DE. I have a concentrated load, you can say, pointing downward, 4 kilonewton. Then we have our vertical reaction for DY. And we know our horizontal reaction for D is 0. Therefore, our horizontal reaction for E is going to be 0 as well. We're going to have a vertical reaction for E, and we're going to have a moment because it's a fixed connection at E. Let's sum the forces in y direction to get the value for vertical reaction at E. So we're going to have dy, we found it already at 6 kilonewton. It's going to be negative 10 kilonewton plus vertical reaction at E all equals to 0. Solving for EY, we get 10 kilonewton as our solution. And then to get the moment about the point E, we need to sum the moments in the E direction or about the point E. We're going to have moment E, and then we have positive because it's counterclockwise 10 kilonewton, and this reaction is 3 meters away, all equals to 0. Solving for moment, we get moment at E equals to negative 30 kilonewton per meter, or it could be said 30 kilonewton per meter clockwise. Okay, we know this is our trapezoidal load, therefore we're going to have to divide this load into its basic components, which is a rectangular uniform load and a triangular distributed load. Now that we have this, we can name the endpoints of this beam here, A and B. Now let's take a moment about the point A. First point we encounter is P, and it's in clockwise direction, therefore negative, and it's L over 3 distance away. Then we have 2P, and it's 2L over 3 distance away. Then we have our distributed triangular load. It's going to be positive because it's in counterclockwise direction. It's going to be W1. We can take L square as common. It'll be W1 plus W2 equals to 5PL. And dividing L squared on both sides, we get W1 divided by 2 plus W2 equals to 5P divided by L. We can subtract the 3P divided by L from 5P divided by L, and simplifying this whole equation we get W2 divided by 2 equals to 2p divided by L. Now we can multiply 2 on both sides, and this becomes 4p divided by L as our solution for W2. And for our W1, all we have to do is plug the value of W2 into equation 2. It's going to be 6p divided by L, take away 4p divided by L, and this comes up to be 2p divided by L. Now we can plug the values that have been given to us. So it's going to be W1 is equal to 2 times 500 divided by 12, and it becomes 8.33 pounds per foot. And our distributed load, the peak distributed load, or W2, is 4 times 500 divided by 12, becomes 166.67 pounds per foot. To solve for this problem, we need to calculate our horizontal and vertical components at A and C. Looking at C, I know that whatever my horizontal and vertical directions are going to be for B, it's going to be for C. To solve, let's first draw our free body diagram for A. And we know, looking at B, there's going to be a diagonal force fraction, which can be converted into horizontal and vertical components. For A, it's a pin connection, therefore it's going to be have horizontal and vertical reactions. And we have a uniform distributed load all along this section AB, therefore it's going to be in the center, 2 meters away, and it's going to be 6 times 4, that's 24 kilonewton. Let's take the moment about the point B. It's going to be 24 is counterclockwise, therefore positive, and it's 2 meters away. And then we can have clockwise AX, which is going to be negative, and it's 4 meters away, all equals to 0. So for AX, we get positive 12 kilonewton. Now we can sum the forces in the X direction. We have negative 12 kilonewton, because we are assuming our vector to be in the negative direction for X. We haven't changed it, we could change it, but it's better to be consistent. And we have positive concentrated load, and we have a positive horizontal reaction for B. Solving for Bx, we get negative 12 kilonewton as our solution. And as said before, whatever our Bx is, it's going to be our Cx. And now we can solve for our vertical component for By. For that, we'll need to draw our free body diagram for point B. At point B, we know that we have already found our horizontal component, Bx, which we found out to be negative 12 kilonewton. We don't know our horizontal component. We don't know our diagonal reaction, FBC. But we do know the dimensions of the structure, therefore we can find the angle. So angle is going to be tan theta 4 divided by 3, which is going to be 53.13 degrees. And now taking tan of 53.13 and By as our vertical component, and we already found our horizontal component. Solving for this, we get By as positive 16 kilonewton. Now we can solve for vertical component for E, but before we do that, we also need to confirm here that whatever our By is our Cy. Therefore, now we have all the component reactions for C. We just need to find vertical component for A in order to finish solving this problem. Now we can sum the forces in y direction, so it's going to be 16 kilonewton. We're assuming negative, and AY, we are assuming positive AY, all equals to 0. And AY is going to be positive 16 kilonewton. For this problem, I'm going to assume all k's are equal to pound. First, let's draw the free body diagram of this whole structure. It's going to look something like this, where we have a vertical reaction AY, and we're going to have a concentrated load right at A, 5 pound. Then we have 8 feet away from A, we have another point load of 7, and then we have 6 feet away, another load of 10, and another 6 feet away, concentrated load of 2 pounds. And down at pin connection B, we're going to have both horizontal and vertical reactions. And from B, about 6 feet away, we have 0.5 pounds of reaction. Okay. To solve this, let's take a moment about the point B. We have 0.5, that's 6 feet away from a reaction. Then we have clockwise traction 2 pound and 6 feet away. Then we have counterclockwise traction 7 pounds and it's 6 feet away. And we have another counterclockwise 5 pounds, 14 feet away. And lastly, our vertical reaction at A, 14 feet away, all equals to 0. Solving for all this, we get 103 divided by 14. It's going to be negative. And solving this, we get our AY as 7.35 kilonewton. Now we can simply sum the forces in y direction. Summing the forces, we get 7.35, take away 5, take away 7, take away 10, take away 2, plus by all equals to 0. Solving for by, we get positive 16.64 kilonewton. And now for bx, other than the point load, 0.5, we don't have any other direction. Therefore, we know if we take sum of the forces in x direction, we will get 0.5 kilonewton as our solution. For this problem, we have 2-member frame and we have to calculate our horizontal vertical reactions at A and C. Let's draw our free body diagram for member AB. For A, we're going to have horizontal and vertical reaction. We have a uniform distributed load, which is 4 meters wide, and intensity is 2 kilonewton per meter. So it's going to be 4 times 2, which is 8 kilonewton, and it will be 2 meters away from point A. And we're going to have horizontal and vertical reactions at B. Let's take moment at the point A. Going to encounter our first concentrated load, 8 kilonewton, and it's clockwise and it's 2 meters away. And then we have vertical component reaction at B, which is counterclockwise, and it's 4 meters away, all equals to 0. Solving for By, we get 16 divided by 4, which is equal to 4 kilonewton. Looking at our free body diagram for AB, we can't really solve for any other reaction until we solve for member BC. Let's draw the free body diagram for BC. For pin connection C, we have horizontal and vertical reaction. For B as well, we can have horizontal and vertical reactions. At the elbow of CB, we have a triangular uniform distributed load. Therefore, we have to take the area of the triangle in order to get the concentrated load of this triangular load. And it's going to be 3 meters. It'll become 18 kilonewton, and it's 2/3 away from B. Therefore, it'll be 2 meters away. Now let's take the moment about the point C. First load we encounter is our 18, and it's 1 meters away from C. Then we encounter our vertical component for By, and it's clockwise, therefore negative, and it's 4 meters away. And we already found the value of 4 By, it's 4. And then for our horizontal component for B is also clockwise, therefore negative, and it's 3 meters away, all equals to 0. Solving for Bx, we get -2 divided by -3, it becomes 0.667 kilonewton. Now that we have horizontal and vertical components for B, we can solve for our horizontal and vertical components at C. Let's sum the forces in y direction. For C, we have negative By, and that is the only other direction other than Cy. Therefore, our Cy is going to be positive 4 kilonewton. Now let's sum the forces in x direction for Cx. And this is going to be positive Cx, negative 18 kilonewton, and positive 0.667 kilonewton, all equals to 0. Solving for Cx, we get positive 17.33 kilonewton. Now finally, we're still missing our x component for A, and we can see that there is no other reaction other than whatever C is exerting on A. Therefore, whatever our Bx is, it's going to be our Ax. Quickly solving for it, we have positive Ax, negative Bx, all equals to 0. Therefore, our Ax is going to be our Bx. That each of the cable will have equal amount of load. That means each cable will be carrying 300 pounds load. Now, let's look at this pulley here, and let's draw the free body diagram of it. So we have a point C here. We have a pulley around it. So we know our pulley is pulling down at point C, and then, the cable is pulling down, and then we also know that cable is also doing reactions in horizontal direction. I'm going to zoom left to right. And since we know our cable is having reaction, therefore C must have counter reactions. Therefore, there's going to be reactions countering the reactions of the cable. Therefore, there's going to be a horizontal component for C, and there's going to be a vertical component for C. Solving this, we know we can sum the forces in x direction at C, and we'll get negative Cx, positive tension force equals to 0. Therefore, our Cx is equal to our tension, and tension we know it's 300 pounds. Similarly, we can sum the forces in y direction. Cy is positive, tension is negative, so this is equal to 0. Therefore, we know our Cy is equal to our tension, and tension is 300 pounds. Now we can look at a broader member, AC. Let's draw the free body diagram of AC. At pin connection A, we're going to have horizontal and vertical reactions. Similarly, we can have horizontal and vertical reaction at B. And finally, at C, we're going to have horizontal and vertical reactions. And we must not forget our pulley system here. So there's going to be reactions because of the pulley as well. It's going to be horizontal and vertical tension. Okay, let's take the moment about the point A. First concentrated load we encounter is Py, and it's 6 feet away. Then we have Cy, 12 feet away, and we have tension from the cable. That's 12 feet away. All equals to 0. Solving for this, we get By as, now we can sum the forces in y direction to get the value of Ay. Solving for Ay, it's going to be negative. We have negative By, but we also have negative from our solution. Therefore, it will become positive. We have negative from Cy, negative 300, and then negative 300 from tension, all equals to 0. Solving for this, we get positive 600 pounds as our solution. we haven't found the value of horizontal reactions at E. To do that, let's sum the forces in X direction. We have positive tension, positive reaction at C, we have a negative reaction at Bx, and we have a negative reaction at Ax. Because we have two unknowns, we can't solve it just yet. Therefore, we'll name it equation 1, and we'll come back for it. Now let's focus on our member dB. Let's draw the free body diagram for dB. Going to have horizontal and vertical reaction at dB. And we have a pulling force from our cable at 300 pounds, and it's 1.5 feet from B. Now let's take a moment about the point D. First point we encounter is our pull force from the tension of the cable, which is going to be negative because it's clockwise and it's 4.5 feet away. Then we encounter our horizontal reaction for B, and it's 6 feet away. And finally we have clockwise reaction for our vertical component reaction at B, and it's 6 feet away. All of this is equal to 0. We already have the value of Vy, and it's negative 1200. Therefore, this would become positive. And solving for Bx, we get negative 975 pounds as our solution for Bx. Before we move forward with dB, let's go real quick to our equation 1 and plug in the value of Bx as negative 975. We get our horizontal component as negative 1275 pounds. Now let's do some of the forces in X direction for member dB. We have negative vertical component, horizontal component at X, and we have positive horizontal component at B. That's going to be negative 975, and then we have negative 300 pound tension pull 1.5 feet away from B, all equals to 0. Solving for dx, we get negative 1275 pounds. And finally, we have to find our values for vertical component at D. Sum the forces in y direction. We have dy, we have by, all equals to 0. Our by, we know it's negative 1200. Therefore, we know our dy is going to be 1200 pound. Now, just to reiterate again, if you get negative reaction force for anything, it just means that you have assumed your vector to be in the wrong direction. It doesn't mean your answer is wrong.